In 1869, the first transcontinental railroad connected America coast to coast. It took 6 years to build. That's the accepted story. But in those same 6 years, workers laid 1,776 miles of track across mountains, deserts, and granite ranges, while simultaneously constructing 689 bridges and boring 15 tunnels through solid rock. That's an average of 296 miles per year, using only hand tools, black powder, and manual labor. The Central Pacific section alone required cutting through the Sierra Nevada, blasting and chiseling 9 tunnels, some over 1,600 feet long, through pure granite. Workers operated in conditions that killed roughly 1 laborer for every mile of track laid. Yet the timeline held. The infrastructure appeared. And within months of completion, entire networks of feeder lines, depots, and rail yards materialized across regions that had been wilderness. The speed wasn't isolated. This is a documentary examination of anomalies in 19th-century rail construction, a topic surrounded by alternative historical interpretations. What follows presents documented facts, official records, and observable patterns. It does not claim definitive answers. It invites you to consider the evidence. The standard narrative tells us railroads emerged from the Industrial Revolution, gradual technological progress creating capacity for expansion. But the construction records reveal something different. Not evolution. Simultaneity. Between 1850 and 1890, the United States built over 163,000 miles of railroad track. Britain added another 15,000 miles in roughly the same window. Russia constructed the Trans-Siberian Railway, 5,772 miles through frozen tundra and mountain ranges, between 1891 and 1916. India's railway network expanded from 0 miles in 1850 to over 25,000 miles by 1900. These weren't sequential developments. They happened in parallel, across continents, in regions with vastly different economies, governments, and technological access. The engineering consistency is what stands out. Standard gauge track 4 feet 5 inches became nearly universal, adopted independently across Britain, the United States, Canada, and parts of Europe. This wasn't mandated by international agreement. There was no Global Railway Commission in 1850. Yet separate nations, working in isolation, converged on nearly identical specifications for rail width, tie spacing, and gradient tolerances. In America, consider the bridges. The Kinzua Viaduct in Pennsylvania, completed in 1882, stood 301 feet tall and stretched 2,053 feet across a valley. It was built in 94 days. The Strucka Viaduct, finished in 1848, required 165,000 cubic yards of stone and still carries freight trains today, 176 years later. These weren't temporary structures. They were built to last centuries, using materials and techniques that seemed disproportionate to the economic needs of their time. Why does a remote valley in Pennsylvania require a stone bridge engineered for loads far exceeding anything 19th century rail traffic would produce? The same pattern appears in terminals. Grand Central Terminal in New York began construction in 1903, but its design assumed electrification, a technology barely viable at the time. The building's steel framework and underground track network anticipated capacities that wouldn't be needed for decades. Philadelphia's Broad Street Station, demolished in 1952, was built in 1881 with similar overcapacity. St. Pancras Station in London, opened in 1868, featured a single-span iron roof 689 feet long and 100 feet high, the largest such structure in the world when completed. These terminals didn't grow into their infrastructure. They started with it. Then there's the labor question. Official records state that roughly 20,000 workers built the Transcontinental Railroad, 12,000 on the Central Pacific side alone, mostly Chinese immigrants. But the math becomes difficult when you account for the work required. Each mile of track needed, clearing and grading the roadbed, laying crossties every 18 to 24 inches, positioning and spiking rails, ballasting and leveling bridge construction, tunnel excavation. The Central Pacific Summit Tunnel, 1,659 feet through solid granite, took 15 months using only black powder and hand drills. Workers advanced roughly 8 inches per day. Yet tunnels of similar length appeared across the American West in comparable time frames, often in regions with minimal documented labor presence. The Hoosick Tunnel in Massachusetts, completed in 1875, stretched nearly 5 miles through the Berkshire Mountains. It took 24 years to finish and killed 195 workers. But dozens of other tunnels, some nearly as long, were completed in a fraction of the time with far fewer reported casualties. The logistical infrastructure moves in lockstep. Rail yards appeared before the cities that would use them. Maintenance facilities were constructed in locations that had no existing settlements. Water towers, coaling stations, and turntables were installed in quantities that exceeded immediate demand. In many cases, the supporting infrastructure predated the communities it served. Cheyenne, Wyoming, didn't exist before the railroad arrived in 1867. Within 2 years, it had a population of 4,000 and a fully operational rail yard with capacity for hundreds of cars. The town was built around the infrastructure, not the reverse. This sequencing repeats globally. In India, the Great Indian Peninsula Railway began operations in 1853. Within 30 years, the subcontinent had over 9,000 miles of track connecting regions that had never been linked by road. The engineering required crossing rivers, jungles, and mountain ranges, yet the construction timeline remained consistent with projects in Europe and America. Were these projects coordinated? Was there shared knowledge? Or does the consistency point to something else, an inheritance rather than an innovation? The physical evidence suggests preparation. The infrastructure didn't just appear in major cities. It appeared everywhere at once. Between 1865 and 1873, the United States added over 35,000 miles of track, roughly 4,400 miles per year. This happened during Reconstruction, when the South's economy was devastated and the North was absorbing war debt. Yet the rail expansion accelerated. Small towns across the Midwest received stations, switching yards, and maintenance facilities sized for populations they wouldn't reach for another generation. The pattern becomes clearer when you examine what was built before it was needed. The Erie Canal opened in 1825, connecting the Great Lakes to the Atlantic. It was 363 miles long, required 83 locks, and took 8 years to complete. The official story credits it with opening the American interior to trade. But the canal's capacity far exceeded the shipping volume of its era. By the time traffic actually required that capacity, railroads had already made canals obsolete. Why build infrastructure a decade before demand justifies it? The same logic appears in Britain's railway boom. Between 1844 and 1847, a period called Railway Mania, Parliament approved over 9,000 miles of new track. Investors poured £200 million into projects that wouldn't generate profit for years. Many lines served rural areas with populations under 5,000. The Settle-Carlisle line, completed in 1876, crossed the Yorkshire Dales through some of the most difficult terrain in England, requiring 325 bridges and 14 tunnels, to connect 2 cities already served by existing routes. It was redundant before it opened. Yet it was built to the same exacting standards as primary trunk lines. The engineering tolerances tell a similar story. Modern rail engineers study 19th-century bridges and tunnels as examples of over-engineering. The Firth of Forth Bridge in Scotland, completed in 1890, used 58,000 tons of steel, enough to handle loads 3 times heavier than anything running on it for the next 50 years. The bridge was designed with wind resistance calculations that anticipated speeds trains wouldn't reach until the 1950s. Who plans for technology that doesn't exist yet? American rail tunnels show the same forward-thinking design. The Hoosick Tunnel, despite its troubled construction, was bored to dimensions that accommodated double-stacked freight cars, a concept that wouldn't emerge until the 1980s. The Baltimore and Potomac Tunnel, opened in 1873, featured ventilation systems sophisticated enough to handle diesel locomotives, which wouldn't appear for another 60 years. These weren't modifications. They were original features. Then there's the administrative uniformity. By 1860, the United States had dozens of independent railroad companies, each privately owned and operated. Yet they coordinated schedules, shared rolling stock, and maintained compatible infrastructure with minimal government oversight. Standard time zones didn't exist until 1883, when railroad companies implemented them unilaterally, forcing the federal government to adopt the system 4 years later. How did competing private companies achieve operational standardization across a continent without central authority? Britain's railways developed similarly. Despite being built by competing companies, the networks integrated seamlessly. The Great Western Railway used broad-gauge track, 7 feet wide, until 1892, requiring custom-built locomotives and cars. Yet even this outlier maintained scheduling coordination and passenger transfers with standard gauge lines. The transition to full standardization took less than a decade, requiring the regauging of over 200 miles of track, completed in a single weekend in May 1892. The coordination required suggests pre-existing frameworks. Storage infrastructure reveals another layer. Grain elevators appeared across the American Midwest in the 1850s and 1860s. Massive wooden structures capable of storing hundreds of thousands of bushels. The first steam-powered grain elevator opened in Buffalo, New York in 1843. By 1870, nearly every rail hub in wheat-growing regions had multiple elevators, each sized for harvests that wouldn't reach those volumes for another 20 years. The Buffalo elevator could process 1,000 bushels per hour. In 1843, Buffalo's total annual grain shipments were under 500,000 bushels. The infrastructure could handle double that in a single season. Within 15 years, it was obsolete, not because it failed but because even larger elevators had been built to replace it. The cycle repeated: build beyond capacity, wait for demand to catch up, then build even larger. Electrical grids followed the same pattern. The Pearl Street Station in New York, opened by Thomas Edison in 1882, powered 85 customers with 400 lamps. But the station's generators were sized for 1,200 lamps, triple the initial load. Within 2 years, Edison was building stations in dozens of cities, each with excess capacity built into the design. London's first power station, opened in 1882 at Holborn Viaduct, could serve 3,000 lamps but started with fewer than 1,000 customers. Why install capacity you don't need? The telecommunications network did the same. Western Union completed the first transcontinental telegraph line in 1861, 8 years before the Transcontinental Railroad. The line required 27,000 poles and 2,000 miles of wire across terrain with no roads, no settlements, and no existing infrastructure. Yet it was operational within 4 months of starting construction. Telegraph lines appeared along rail routes before the rails did. In some cases, telegraph poles were placed in locations where track would be laid years later, positioned as if the route had already been surveyed. Water systems show identical forward planning. The Croton Aqueduct in New York, completed in 1842, delivered 90 million gallons of water per day to a city consuming less than 60 million. The aqueduct ran 41 miles, crossed valleys on stone bridges, and tunneled through hills, all to deliver surplus capacity. Chicago's water intake tunnels, built in the 1860s, extended 2 miles into Lake Michigan and could supply a population of 1 million. Chicago's population in 1860 was 112,000. The infrastructure anticipated growth that hadn't started yet. Sewage systems followed the same logic. London's sewer network, designed by Joseph Bazalgette and completed in 1875, used 318 million bricks to build 1,100 miles of tunnels. The system was sized for a population of 4 million. London's population in 1860 was 2.8 million. Bazalgette's design included overflow capacity, redundant pumping stations, and treatment facilities that wouldn't be fully utilized until the 1920s. He built for a city that didn't exist. Whether this reflects inherited knowledge, coordinated planning, or independent convergence remains open. But the consistency across nations, technologies, and decades suggests a pattern larger than individual innovation. The infrastructure arrived before the need. And in many cases, the need never fully caught up. The term Tartaria appears on European maps from the 15th through 19th centuries. It referred to the vast territories of Central Asia, Siberia, and parts of Eastern Europe, regions largely unknown to Western cartographers. The name derived from Tatar, the Turkic and Mongolic peoples who inhabited these areas. It wasn't a single empire. It was a geographic designation for lands beyond European control. By the late 1800s, the term faded from maps as these regions were surveyed, colonized, and incorporated into the Russian Empire and other nation-states. Tartaria disappeared from atlases not through suppression, but through specificity. Better mapping replaced vague labels with actual place names. In modern alternative historical discourse, Tartaria has been reinterpreted. It now represents a hypothesis that a technologically advanced civilization existed across Eurasia and was either destroyed or deliberately obscured from historical record. Proponents point to architectural similarities, infrastructure anomalies, and gaps in conventional timelines as evidence. The rail infrastructure sits at the center of this reinterpretation. Three models attempt to explain the patterns. The first is conventional history. Rapid industrialization driven by coal, steam power, and capital investment created the conditions for explosive infrastructure growth. The over-engineering reflects Victorian ambition and the absence of modern cost-benefit analysis. The simultaneity across continents resulted from technology transfer, shared engineering knowledge, and parallel economic pressures. Under this model, the anomalies aren't anomalies, they're the expected outcomes of industrial capitalism encountering virgin territories. This explanation accounts for most of the evidence, but it struggles with timing and scale. The second model suggests inherited infrastructure. Under this framework, the 19th century rail boom didn't create networks from scratch. It restored or repurposed existing systems. The overcapacity, the forward-thinking design, the administrative coordination, all remnants of a previous civilization's transportation grid. The construction records describe renovation, not original building. The labor shortages, the impossible timelines, the engineered for future loads bridges, all make sense if the foundation already existed. This model explains the consistency and the scale. But it requires a prior civilization for which mainstream archaeology has found no supporting evidence. The third model proposes coordinated advanced knowledge. A group, governmental, corporate, or otherwise, possessed surveying data, geological maps, and long-term population projections unavailable to the public. They built infrastructure not for current needs but for planned expansion. The overcapacity wasn't excess, it was intentional staging for controlled growth. The simultaneity across nations reflected cooperation hidden behind the facade of competition. This model explains the planning and the coordination, but it requires secrecy maintained across decades, continents, and competing powers. Each framework has explanatory power. Each has gaps. The year 1816 appears in multiple contexts. Globally, it's remembered as the year without a summer, caused by the eruption of Mount Tambora in 1815. Crop failures spread across the northern hemisphere. Famine followed. Populations migrated. In historical records, 1816 marks a rupture. The world before looks different from the world after. In the decades following 1816, infrastructure projects accelerated worldwide. The Erie Canal began in 1817. Britain's railway expansion started in the 1820s. Telegraph networks, water systems, and urban redesigns all emerged in the same narrow window. Whether this timing reflects recovery from catastrophe, opportunistic rebuilding, or something else remains interpretive. The infrastructure itself doesn't declare its origins. When we talk about Tartaria's rail infrastructure, we're using metaphor. We're describing a pattern that resists easy explanation within conventional frameworks. The term becomes useful not because it names a specific civilization, but because it acknowledges the pattern's existence. The evidence invites examination without demanding conclusions. Stone bridges built to last 500 years. Tunnels bored to dimensions exceeding their era's needs. Administrative systems coordinating across competing entities. Capacity installed before populations arrive. These aren't disputed facts. They're documented, measurable, photographable realities. What changes is the interpretation. You can stand inside the Hoosac Tunnel today. You can measure its dimensions. You can read the construction records, count the reported casualties, calculate the advance rate through granite. The tunnel exists. The numbers exist. What's debated is the story connecting them. The same applies to the Fourth Bridge, the Transcontinental Railroad, the grain elevators of Buffalo, the telegraph lines crossing the plains. The physical evidence remains constant. The narrative is what shifts. Some see industrial ambition. Others see inherited systems. Still others see coordinated planning masked as competition. All three perspectives work with the same evidence. All three must account for the same anomalies. And all three remain ultimately interpretive frameworks imposed on data that doesn't fully conform to any of them. The rail infrastructure of the 19th century doesn't prove a lost civilization, but it does resist the seamless explanations we've constructed around it. The timelines compress uncomfortably. The engineering seems prescient. The coordination appears unlikely. And the capacity precedes the need with suspicious regularity. Whether that pattern reflects inheritance, planning, or simply the chaotic efficiency of industrial capitalism colliding with empty land, that remains the question. The tracks are still there. The bridges still stand. The tunnels still cut through mountains built to accommodate trains that didn't exist when they were bored. The evidence doesn't demand a specific conclusion. It simply asks that we look at what was built, when it was built, and how quickly it appeared across the world. And then it asks, does the accepted timeline fully account for what we can still see? The answer depends on which anomalies you're willing to accept, which patterns you're willing to notice, and which questions you're willing to leave open. The infrastructure waits. Silent. Functional. Older than it should be, larger than it needed to be, and more coordinated than competing interests should have allowed. It doesn't explain itself. It just exists, solid, measurable, and stubbornly resistant to simple stories.